Welcome to AI Paper Slop, the YouTube series where we summarize the latest AI and tech papers. Today we are diving right into AHA-WAM, which is, well, the full title is Asynchronous Horizon Adaptive World Action Modeling with Observation-Guided Context Routing.
Yeah, it's definitely a mouthful, but the researchers, this is from Shanghai Jiaotong University, Baidu AI Cloud, HKU, and the Shanghai AI Lab, they've identified a really fundamental flaw in current robotic world action models.
Right, the WAMs.
Exactly. Because right now they force this long-term world prediction and the real-time action execution to run synchronously, like at the exact same temporal resolution.
Which is a huge bottleneck.
Yeah.
And AHA-WAM solves this by introducing a dual diffusion transformer, or DiT architecture, right? So it physically decouples the slow, low-frequency world planner from the fast, high-frequency action executor.
Yeah, and it routes the context between them asynchronously. The result is just, it's wild. It hits 24.17 hertz closed-loop control. It's a 4.59x speed up over fast WAM.
Almost 5 times faster. That's massive.
It really is. And it achieves state-of-the-art zero robot data pre-training success rates. We're talking 92.80% on RoboTwin and 78.3% in the real world.
So now that you sort of know what AHA-WAM is, we really need to look at why it was built in the first place by looking at the bottleneck in current generalist manipulation policies, like specifically VLAs.
Right, the vision language action models.
Yeah. I mean, we know VLAs like RT1, RT2, Pi0, they scale imitation learning incredibly well, but the action labels just offer really sparse supervision for the actual physical dynamics.
Yeah, action labels give you basically zero feedback about how the physical scene actually responds to things like contact or gravity. So the field shifted toward world action models to fix this by coupling action prediction with dense video-based world modeling.
To give it that dense physical prior.
Right. But existing WAMs either explicitly roll out future frames, or they just couple world and action modeling on the exact same short horizon. If we connect this to the bigger picture, it forces the world branch to just waste parameter capacity modeling these redundant near-term frame variations.
Right, because adjacent frames at 24 hertz are highly correlated and just weakly informative for control. It's kind of like trying to play a highly strategic game of chess, but your brain forces you to use your primary conscious brain power to micromanage the twitch of every single individual muscle in your arm.
That is exactly it. It's a structural mismatch and temporal abstraction.
Yeah.
You're burning compute predicting tiny pixel shifts instead of forming a real plan.
Okay, let's unpack this. Let's look at the actual architecture, because the hardware footprint of the separation is it's heavy. The dual DIT setup has the video branch sitting at 4.99 billion parameters.
Almost billion.
And then the action DIT is 1.02 billion parameters, plus a 1.22 billion parameter memory and context routing module.
Yeah, it's huge. But the division of labor makes it work. The video DIT is the planner. And since it's temporally decoupled, it runs at a low frequency. It just maintains this rolling key-value memory over past observations.
And it exposes that reusable, layer-wise latent context, right?
Exactly. It encodes long horizon scene evolution, so it amortizes those really expensive world model computations across multiple action steps.
Got it. And then the action DIT is the executor.
Right, operating completely in parallel at a high frequency. It executes short action chunks in a closed loop, and it queries the planner's context through layer-wise joint attention.
Okay, but wait. If these two massive transformer models are operating at entirely different frequencies, how do they avoid essentially desyncing?
What do you mean?
Like causing the robot to execute an action based on outdated world context. The arm moves, the object shifts, but the planner is stuck on a visual state from a second ago.
Oh, right. Yeah, that staleness is the whole crux of the asynchronous problem. And solving it took two major innovations: Horizon Adaptive Offset Training and Observation-Guided Video Context Routing, or OVCR.
Okay, let's break those down, starting with the offset training.
So during training, and they use a joint flow matching objective here, Horizon Adaptive doesn't actually mean online horizon adjustment.
Oh, so it's a horizon decoupled formulation.
Precisely. They mathematically sample an offset delta. This basically teaches the action DIT how to consume the long horizon planner context under totally variable action start offsets.
Oh, I see. So the action executor learns to interpret the context no matter where it randomly lands in the planner's slower cycle.
Exactly. It handles the training alignment perfectly. But delta sampling during training doesn't fix the real-time physical staleness during inference. The planner's KV cache is still stale relative to the immediate visual feed.
Right. The real world keeps moving.
Yeah, and that's where OVCR comes in. Because static caching just outright fails in high-frequency closed-loop control. OVCR dynamically constructs chunk-specific latent video context from the current observations.
Wait, if it's processing the visual feed dynamically to create routing queries for every single high-frequency step, aren't we just reintroducing the latency bottleneck? Like you're injecting a massive math operation right back into the critical path.
You would be if they routed it through the 5 billion parameter backbone, but they don't. OVCR uses a super lightweight visual projection module.
Ah, okay.
Yeah, it maps the instantaneous spatial tokens directly into the latent dimensions of the planner's context.
Yeah.
These become observation-conditioned routing queries.
So it looks at the stale context, takes this lightweight visual query, and computes a delta to patch the KV cache.
Exactly. It's a gated residual update. The heavy video DIT stays totally outside the per-update critical path. But thanks to OVCR, every action chunk gets a planner representation perfectly aligned with the latest visual evidence.
Wow, it's just a brilliant bypass. But, theoretical architecture is one thing. Actually hitting 24.17 hertz on physical hardware with 7 billion parameters requires serious CUDA optimization.
Oh, definitely. Eager execution in PyTorch would completely kill your latency.
Right. And you mentioned that staggering inference speed up at the top. They took a 10-step action inference latency from 415.77 milliseconds in PyTorch down to just 41.37 milliseconds.
Yeah, a full 10x reduction. And they achieved it practically without altering the model weights or the sampling procedure.
How? How do you drop it by an order of magnitude just through systems engineering?
So they hit the CDA acceleration from 3 different angles. First was graph-level static capture. They compiled the backbone modules, the action DIT, the memory modules, the AE into TensorArt engines.
Okay, so that gets rid of the Python dispatch overhead.
Right, they replay the fixed denoising loop with CUD graphs. The GPU doesn't have to wait for the CPU anymore. But you can't statically capture the video DIT prefill path because of Python side control flow.
Right, because it only runs when a new long horizon chunk is actually needed. The path diverges dynamically.
Exactly. So that brings us to step 2, selective torch.compile. Since full trace export is impossible there, they selectively applied it just to the prefill path.
Which gives them JIT-compiled kernel fusion, where static graphs just won't work.
You got it. And the third pillar is hot path redundancy elimination.
Because diffusion is basically entirely memory bandwidth bound.
Yeah. So they manually hoisted chunk-level computations outside the denoising loop, and they completely skipped repeated host-to-device tensor copies for anything that stays fixed across the denoising steps.
It's just meticulous. Okay, here's where it gets really interesting. Does this massive speed up actually translate to better task success?
Well, let's look at the benchmarks. On RoboTwin 2.0, AHA-WAM hits 92.80% average success.
Which beats Lingbot VA at 92.24%. FastWAM at 91.83%, and Modus at 87.84%.
Exactly. And it massively outperforms Pi0, which was stuck at 79.75%.
And again, AHA-WAM had 0 robot data pre-training, but simulation is clean. What about the real-world deployment?
Right. So they tested 4 real-world physical tasks: store plate, organize desktop, fold towel, and prepare soy milk.
Which requires really precise force feedback.
Yeah. And AHA-WAM achieved 78.33% success in the original settings.
Which is huge, because Modus completely fell apart there, down to a mere 21.67%. FastWAM was at 68.33%, and AHA-WAM essentially matches the heavily pre-trained generalist VLA Pi0, which hit 76.67%.
But the generalization shifts are where the data gets really nuanced. They changed lighting, altered textures, moved the robot to a novel environment. And under those shifts, Pi0 does edge out AHA-WAM in pure binary success rate.
Which makes sense mathematically, right? Pi0 has massive internet-scale pre-training.
True. But AHA-WAM achieves the highest progress score at 35.00.
Ah, because progress score actually measures how many subtasks within the sequence were completed, even if the absolute final goal failed.
Right. This raises an important question. What does this deployment stability actually prove? It proves asynchronous world action modeling works. The long horizon context ensures task progress. It remembers the overall plan.
Right. Well, the high-frequency execution of the action DIT allows for real-time physical corrections when things like friction change unexpectedly. It doesn't just freeze up.
Exactly. It delegates the immediate response to the fast executor.
Which proves we just don't need to force world models and action models into the same temporal bottleneck.
No, we don't. Synchronous WAMs are a dead end. Decoupling lets you scale the world model without destroying latency.
It's a really profound shift in embodied AI. And, when you step back and look at this architecture, I want to leave you with a final thought to mull over. AHA-WAM is strikingly similar to human biological motor control.
Oh, that's interesting.
Yeah. I mean, think about it. The video DiT acts like the cerebral cortex, right? Making slow, long-term plans. While the action DiT functions like the spinal cord and the cerebellum.
Executing fast, closed-loop reflexes without constant conscious oversight.
Exactly. If you touch a hot stove, your spinal reflex pulls your hand back instantly. It doesn't wait for your cerebral cortex to calculate the exact thermal dynamics of the burn.
It relies on localized updates.
Right. So if this asynchronous architecture is what finally breaks the latency bottleneck, maybe the future of physical AI isn't about building one perfectly synchronous brain. It's about evolving a hierarchical, asynchronous nervous system.
That is a really brilliant way to frame it.
Well, thanks for joining us for this deep dive into AHA-WAM on AI paper slop. We highly encourage you to pull up the full paper, check out the flow matching math for yourselves, and we'll see you on the next deep dive.